Is it better now?
All right, great. Yeah, sorry about that. We are recording now. Yeah, like I said, this is track 2. Track 1 happened about started an hour ago. And that track's covering the great work out of Professor D.K. Panda's group at the Ohio State University. This track number 2 has 4 sessions. The first 2 will cover UCX and OFI libfabric, which we'll hear all about, but very roughly speaking, are transport layer software libraries, ubiquitous in HPC middleware, and many more distributed programming models. The 2 sessions after that cover research in microservice architectures, which is pretty exciting as it's a completely new topic for the Hot Eye tutorials. So let's get started with the first session. This is the UCX Unified Communication X Framework session. Let me introduce the authors. There are quite a few, so I will, introduce them, with an abridged version of their bios. But if you'd like to see all the gritty details, they are on the session webpage in the Zoom events pages. So first we have Jeffrey Young. Jeff is a senior research scientist at Georgia Tech School of Computer Science. His background in computer architecture and his research interests focus on the intersection of HPC and novel accelerators, including GPUs, Xeon Phi, FPGAs, and ARM SVE processors. He's co-director for Georgia Tech Center for HPC and is also the director of a novel architecture test bed, the Rogues Gallery, which sounds pretty cool and aims to simplify and democratize access to novel post-Moore architectures and accelerators. He received his PhD in computer engineering from Georgia Tech and has led multiple tutorials and workshops in multiple venues, including supercomputing, ISC, and many more. Second, we have Yossi Itigin, who is the communication middleware team leader at NVIDIA and is the maintainer of the UCX code base. Yossi participated in last year's Hot Interconnect's UCX tutorial and has over 8 years of experience in working with networking communication protocols at Mellanox and more recently at NVIDIA, of course. Third, we have Matt Baker. Matthew Baker is an R&D staff at Oak Ridge National Lab. Is that still true? Sounded like maybe this bio is out of date.
Yeah. Yeah, I mean, a lot of the bio is still accurate, but I jumped from Oak Ridge to a startup called Voltron Data.
Oh, very cool. Okay.
So yeah.
Well, yeah, it sounds like, yeah, the rest of the bio is accurate then. After graduating from East Tennessee State University, he went on to do research at Oak Ridge. He's been doing research in benchmarks, system languages, interconnect programming libraries, and CPU simulators. He's one of the developers of UCX for Eugenie, UCX Pi, and on the team that implemented Blazing SQL over UCX. His main interests are in parallel programming languages and communication libraries like OpenSHMEM. Matt Baker has also organized past OpenSHMEM workshops and has presented his work at various other venues. Fourth, we have Oscar Hernandez, who has a PhD in computer science and recently joined NVIDIA Mellanox in 2021 after working for 12 years at Oak Ridge National Lab, where he was a senior staff member of the Programming Systems Group, which does research on programming models, compilers, and tools that are deployed at supercomputers like Summit and Frontier. At Oak Ridge, he helped standardize parallel languages and APIs for accelerated nodes such as OpenACC, OpenMP, and communication libraries and frameworks like OpenSHMEM and UCX. Oscar has experience giving tutorials at different venues like Supercomputing ISC, the Exascale Computing Annual Meeting, and for NSF. And last but not least, we have Chris Taylor. Chris is a senior research scientist at Tactical Computing Labs, where he develops runtime system software, simulation software for HPC systems, and data analytics / machine learning software. He has over 15 years of experience in modeling and simulation, data analytics, machine learning, and HPC runtime systems. Chris has contributed to Stellar HPX, Chapel, developed patentable technologies under DARPA Cyper Fast Track, and created a public domain machine translation service for Crisis Commons supporting NGO responses to the 2010 Haitian earthquake. Wow, that's cool. Chris has a master's in computer science from Georgia Tech and a bachelor's in computer science from Clemson University. So we obviously have a very experienced crew here today, and they will lead us in a tutorial on UCX. Before handing it off, I just want to remind folks that we are trying to use Slack, and there's a separate channel for each tutorial session. I believe this one is at the very bottom of the list, at least it is in my window, and it's named Tutorial Unified Communication X, etc. So please take it away. I assume, Oscar, you'll be leading us off?
Yes, thank you, David, for the introductions. Welcome, everybody, to the UCX tutorial at HOTI 2022. I want to give you a welcome remarks on behalf of the UCF consortium and Gilad Shiner as the president. As you know, UCX is part of this UCF consortium, which has the mission to develop open standards and communication frameworks that target data centers. And it's an effort that is being developed in collaboration with the industry, laboratories, and academia. And the use cases are for applications that are data-centric, machine learning, AI, and high-performance computing codes. The UCF consortium hosts several projects and working groups, and UCX is one of the main ones of those of the organization, and it was also the first one, which focused on point-to-point, low-level communication framework that supports a variety of network technologies, but also has sisters projects like the UCC project, which is a collective library that also has that focus on collective operations, and as well as other projects that focus on providing a UCX for Spark. So this is the Spark UCX project. Then we have other projects like OpenSnappy that focus on exploiting offloading and compute capabilities of smart networks, including DPUs and so on. And what the organization also has efforts in the context of benchmarking, developing benchmarks that can measure also the performance for smart networks and all these technologies and so on. The organization is formed by several organizations, including NVIDIA, Los Alamos, AMD, Ohio State, Argonne, IBM, and ARM, and it has a board, has board members that they meet once a month to discuss the direction of the projects. And if you have more, if you are more interested in getting more information about the UCF consortium, that's the link. So UCX started in 2012 as a research effort as the national labs that started in collaboration with the industry. In this case was Mellanox, and it's a small group of people that developed great ideas that came together, and over the last decade it has grown significantly, and it's been as basically as one of the main technologies that's being deployed at data centers and also at very large scale supercomputers, and is currently available, basically widely available in systems and so on. And we have also a great community and that has grown over the years. UCX, the history comes from the idea of creating a low-level communication framework that took the best of the worlds for technologies developing the last decades, starting from LAMPI and OpenMPI, where certain concepts were adopted, like a modular design architecture, network layers, as well as vendor-specific low-level communication libraries like PAMI from IBM and MXM from Mellanox, where lessons were taken from those low-level communication APIs, as well as a research project from Oak Ridge National Laboratory called UCC, which focus on low-level optimizations. And all of these ideas and concepts that were developed over the last decades were consolidated and brought together into the UCX project. And that's what has led to a low-level performance communication framework that focuses on performance portability, scalability, and efficiency. The idea of UCX is that we want to provide a high-performance universal data move across architectures. For example, to move data from the memory of a host, like a CPU, to another memory of an accelerator or a device like a GPU or a TPU, in a way that is portable, performance portable, to move the data, and that can also support multiple programming models that UCX can be used to implement multiple programming models and frameworks, and such as MPI, PGAS, languages, machine learning, AI frameworks, data analytics, storage, and DPUs APIs. The design of UCX, although we're going to cover this more in detail in the tutorial, one of the design choices was to provide a two-level API, a very high-level API called UCP, and a low-level API called UCT. And the difference is that the low-level API focus on APIs that are close to the hardware or the transport available in the hardware, and the high-level API is focused on protocols that are available or are needed by the programming models. And this idea of having a low-level and high-level API was created at the beginning to give us flexibility to implement programming models, but also provide uniform support across the different network technologies, and also opens the door for co-designing functionality and activities in both the hardware and the programming models as well. So currently, UCX is supported on a variety of architectures, including x86, Power 8 and 9, ARM, V8, and there is also some work in progress to support RISC-V, which we will cover a little bit in the tutorial. And it can be used also in a variety of systems and platforms. Basically, that goes from a Raspberry Pi all the way to supercomputers that deploy it. And also, UCX is also aware of accelerator and devices like GPUs and can also be used for DPUs and so on. So the breadth of the deployment of UCX is wide, and it can be available on all of these systems and different architectures. One of the important things about UCX is that this adoption has been quite high in the context of programming models. It has been adopted to implement MPICH, OpenMPI, NVIDIA HPCX, Huawei MPI, as well as PGAS, GasNet implementations, and as well as OpenSHMEM in the OpenSHMEM reference implementation, as well as the OpenAPI SHMEM and Sandia SHMEM, as well as runtimes like Charm++, data analytics frameworks like NVIDIA Rapids via Dask, and NVIDIA's and Nickel collectives libraries that supports collectives on multiple GPUs. The UCX has been tested and deployed in all these architectures and all these programming models because we focus significantly on testing to make sure that every release is tested significantly so that it works and can be used in production. And we take a lot of pride in the context of testing and making sure that things are stable enough and performant for each of these releases. As you know, UCX has a large community and has and it's also being hosted by the UCF consortium, where we meet every year. And UCX also won the R&D 100 award in 2019 as one of the innovative projects where that has been adopted by the industry and as well as academics and national laboratories. Here are some links on the official website for UCX and the mailing list. And if you are interested in learning a little bit more about the documentation of UCX, there's a link there as well as a contributor agreement if you're interested in contributing to the project. So here, Yossi is gonna give us an update on what is the latest and greatest in UCX as today. And he's gonna go over basically what's new.
Hello, everyone. So I'd like to say what we already merged to the master branch this year. So we have Golang bindings in addition to Python and Java bindings. Also, we added support for static link, which means that now you can build your application and link it statically along with UCX, and all the issues that were related to initialization and dynamic constructors were resolved. We improved the GPU memory protocols for better performance for different cases of host memory, device memory, and intranode communication, and so on. Also, as part of supporting DMA buff and also improving performance for zero copy, we moved the registration cache from a lower level from UCT to the upper layer, UCP. And next part is going to remove it completely from a UCT layer. Also added a few API extensions. First one is to allow passing a user memory handle, which can bypass memory registration or a registration cache lookup altogether. API to set a source address for client-server connection, so you can say which device you're going to initiate the connection from. It is helpful if there are a few TCP/IP devices on the system. Also works with RDMA CM. Also added API to query data type properties. For example, if you create some data type with UCX, you can query its size, extent, and so on, and the packet size. Also extended the statistics and the introspection by a virtual file system with a fuse that you can mount on the same machine that is running UCX. It would show all UCX internals, variables, configuration, and many more things. In addition, we reduced the remote key size on the UCP layer to make memory utilization more scalable for PIGAS SHMEM applications. And that's it for the main things.
Thank you, Yossi. And with that, we conclude this very brief overview, and we make it available, the presentation to Jeff to get started. The rest of
all right. You want me to take over sharing, Oscar?
Yes.
Okay. All right. Thank you everybody for joining us. So we went through the kind of the high level introduction. So if you only had 10 minutes to learn about UCX, then what Oscar and Yossi shared hopefully is a good introduction to why you would actually want to interact with UCX. What we'll go into here is more detail. So this is sort of the longer version of the tutorial. One thing to point out, these slides should be available on the GitHub site that we have here. So this is github.com, gt-crunchrg, and then look for the UCX tutorial. We do have the old version of the tutorial from last year. A few things have changed, so the updated slides should be there. Obviously, I think David also mentioned that if you want to ask questions, you do probably need to do that in the Slack channel just because of the way Zoom events works. Some other resources, read the docs for UCX, and then the mailing list. So if you start using UCX and you have questions, those are good places to reach out to. A lot of the folks on this tutorial, are available there. Okay. So just briefly, let's go through the agenda. So we went through kind of the ecosystem introduction. I'll be going through, what we consider kind of the basics. So part of that is, what are some of the sort of necessary pieces that you might need, including a little bit of a background on a one-sided and RDMA style communication, and then talking about sort of the high-level UCX API. I will be working mostly with the Unified Communication Protocols, so that's UCP, and then we'll have some other interesting stuff later on. Kind of in the middle, we have a few demos that Matt will help lead. The example code for those is in the repo. We tested them locally on a few Ubuntu and RHEL machines. We can't guarantee that they work out of the box, but if you want to try and pull them and follow along, you're welcome to do that and ask questions about those during the tutorial. We'll also talk about GPU UCX Pi implementations, and later in the tutorial, Chris is going to tell us a little bit about some of the work that he's done to add UCX support to RISC-V platforms, including the Sci5 unmatched board. Finally, we're going to talk a little bit about some very advanced stuff. So Yossi is probably one of the foremost experts in UCX, I would say, and he's going to talk a little bit about some of the bindings and how you would use UCX to implement something like OpenMPI. The slides do have some additional information on what we would consider kind of advanced topics, but those are things that we'll kind of leave to the tutorial attendee to kind of figure out later on. All right, so why are you here? Obviously, with hot interconnects, you're interested in figuring out, so what is the latest and greatest in terms of using interconnects, different types of interconnects that are used at a small scale, kind of on chip, all the way up to very large systems. UCX specifically is probably focused more towards the right side of this figure here. Obviously, the server up to mini servers types of implementations. But before we get into exactly why we need UCX, we'll do a little bit of background. We'll talk about basically a few RDMA concepts, one-sided copy, things like that. So here we have sort of a traditional TCP/IP stack with Ethernet on the left-hand side. On the right-hand side, we have something like InfiniBand, which we consider to be sort of more advanced and kind of more suitable for high-performance computing type applications. Obviously, the layers look very similar, except for the application layer. They have almost the same names, but there are things that are a little bit different. Most significantly, you'll notice on the right-hand side that the transport layer down to the physical layer can all be accelerated in hardware with something like InfiniBand. Whereas with a traditional Ethernet, excluding something like RDMA over converged Ethernet, on the left-hand side, a lot of these layers actually operate in software, so they tend to be much slower. Okay. There are a few communication models that we think about when we think about high-performance interconnects, like InfiniBand. The sort of traditional one is sort of a two-sided communication model where you send some data and then you get some ACK back that receive the data. There's also one-sided communication model where you do an RMA, or remote memory access, or something like an atomic operation. In this case, typically you're setting up some kind of buffer protocol using something maybe like a rendezvous protocol where you're saying, okay, let's exchange some metadata, set up a buffer, and then we'll just kind of use either a put or get or possibly an atomic type operation to exchange data. This second type of communication model is what we're really interested in for HPC interconnects. And part of that is because, in that previous figure I showed, there's a lot of software overhead that happens. with all the layers of the stack, and then also with kind of the service calls that happen with the operating system. So just to show you what we mean by that, if you have sort of a traditional application, think again about that Ethernet TCP/IP type of implementation. On the left-hand side here, you have something where your application is saying, okay, I need to send some data. I'm initiating a call to some kind of kernel driver, and then that is potentially helping me, set up and initiate a transfer to a remote buffer or from a remote buffer. On the left-hand side here, you have not only the initialization and a query phase, you also have a system call every time that you need to send and receive data. On the right-hand side, when we say OS bypass, what we really mean is that we're sort of setting up that initial buffer once, and then in subsequent calls to either, send, receive, or get data to that buffer, we're just bypassing the operating system. So we're not doing any more system calls in that second scenario. So there are two types of RDMA communication modes that we need to understand how they're used with UCX. One is zero copy. That's basically where the sender, does that initiation and tells the receiver, okay, that I'm gonna send you some data. The receiver basically specifies a buffer, where it wants the target data to end up at, and that is kind of the final destination in memory, basically. And once that initiation is complete, then the sender will send the data, the receiver will place it in its final destination buffer, and then the transaction is complete. So this is something that's really good, say, if you have to send a very large message. But you can imagine if you did this much sort of setup for, a lot of small messages, then that might not be very efficient. For that case, there's something called buffer copy, where you have a temporary buffer that is on both the sender and receiver, and then that requires one extra copy to move, typically a small chunk of data from the receive buffer to its, memory address location that's accessible to the application. So there's kind of a trade-off if you have something that you want to be sort of latency optimized or bandwidth optimized. You can pick one of these two types of communication modes. So just to illustrate that, here's a picture that shows the zero copy. So again, we have our RDMA specification of doing data transfer versus something like TCP/IP, which is the kind of gray arrows here. So on the left-hand side, you see, with something that is sort of software driven. In the TCP/IP case, you're copying data from the application's memory data buffer. You're creating a socket, you're passing it through the TCP/IP protocol, then sending it through an OS layer, and then sending it via the NIC to the remote node, and then replicating everything on that side. Whereas ideally with RDMA, we would skip a lot of those steps once we do the initialization phase, which does take a little bit of time to set up. But typically if you're doing a long-running transaction for an application, this will always be much more efficient. Okay. And there are a lot of different operations that you can do with high performance interconnects. You can obviously do read write. You can do something that is like send receive, where you have sort of an equivalent buffer, and like a good example is if you're thinking about kind of an MPI style send, where you're setting up sort of a symmetric buffer on both sides of your connection, and then you're sending some amount of data either via small packets that get kind of reorganized and then placed into the appropriate memory region. Or you can do things like very small operations, like you can do atomics, where you say take a value and you swap a remote value and a remote memory address with the sender's value. Then there are things like group communication, where you have sort of a one-to-many or a many-to-one type operation. All of these are things that we would like to be able to do efficiently with an RDMA style interconnect. So that brings us to our stack again. So previously we looked at kind of a basic TCP/IP stack. We looked at the InfiniBand RDMA stack, and here is sort of a simplification of what that looks like, including the hardware pieces of things. So down here at the bottom, we have the transport layer, and then probably a little bit of the physical layer as well, because we have the driver and the I'm just checking on the Slack here. So, okay. I'll answer your question in a second, Sissy. Thanks. But basically you have your applications, then you have something like a programming model. So you have sort of traditionally two-sided, possibly one-sided MPI, or something like a SHMEM or UPC type language that supports PGAS, put-get type operations. Then you might have something like a middleware layer. So examples of this that we show here, GasNet, ARMC, these are things that support kind of RMA style operations and software. And then of course you have a variety of drivers and different types of hardware. So kind of the key thing that we're focusing on here is this communication middleware layer. So that's sort of one source of potential improvement that we can make. So digging in a little bit deeper in that, if we look at something like a traditional RMA put operation, and this is, let's just say, an InfiniBand, style put operation from several years ago, that might take something like 650 nanoseconds, and a lot of that is actually the middleware. So what we would like to do is we'd like to decrease that so that we can keep our latency lower than a microsecond, which is typical for HPC hardware. But obviously, if we're adding a lot of software overhead on top of that with some other kind of middleware, then we're losing efficiency. So this is sort of the motivation for implementing something like UCX. On the right-hand side here, we see an example improvement. This is not specific to any one architecture, but something that is maybe a 5 to 6x improvement in latency. Okay. This slide here is kind of just showing there is a huge variety of different types of interfaces that we have to worry about. So that's the other issue, is that we want something that's low latency, but everyone has their own, programming model. They have their own hardware, and they typically have their own API to operate on top of things. So we have a question in the chat says, what's the difference between NVLink versus UCF? So UCF is actually, just to clarify, UCF is the foundation that maintains the unified Communication X stack. So I think your question is maybe what's the difference between NVLink and UCX? UCX is kind of the combined middleware, high-level kind of driver interface, whereas NVLink is actually the hardware that NVIDIA supports. So if we say something like Mellanox InfiniBand, the hardware for that is very similar to something like NVLink. But the main takeaway from this is not that we need to worry exactly about all these, but just that there's a wide variety of different types of interfaces. So if we dig down into some of the benefits and disadvantages of each of these, we have a couple of different categories. We have things like vendor-specific APIs. So these are things like InfiniBand verbs. Obviously, they're very optimized for performance with that system. They tend to be pretty high quality. The issue, again, let's just use verbs as an example, and not necessarily picking on it for any particular reason, but InfiniBand verbs is really only going to work on a Mellanox or now NVIDIA type hardware. Obviously, too, if you're thinking about kind of mixing different types of interconnects, this is a little bit more challenging. A good example of that is if you have an NVIDIA GPU that is a PCI Express GPU and you plug it into an Intel system, it's really difficult to get them to agree and support features like GPU Direct. And some of that is just because the interconnect protocols and APIs are very different. On the other hand, we have things like open source APIs. So if we think about like a programming model, this might be something like mVapage, which is being covered in the other tutorial running right now. These tend to be, pretty high quality, very easy to pick up and use, very good as a research platform. I think the downside is that they don't necessarily have all the details of the low-level hardware implementation that vendors do. And then again, it's always kind of a battle to support new hardware with these APIs and libraries. Finally, we have things like research APIs. So on our list, a few slides back, we said something like portals, which is a project run out of Sandia. And that's a really interesting, innovative kind of network interface. It's very forward-looking. I think the downside is that vendors may not be that interested in fully supporting them. So it's really on the research organization or the group to kind of support. Okay. So if we think about all these different interfaces, the key spot that we want to hit is something that supports kind of the vendor specific middleware, something that incorporates the best qualities of open source software and middleware, and also that allows us to do some kind of research oriented investigation of middleware. So that's where we get UCX. The mission of UCX is kind of to bring together these three groups: the vendor, the research oriented, and the open source community, to build something that is both high performance, extendable, and usable. There are a lot of kind of features here in the mission, but the key thing is this box down at the bottom. We'd really like to support better co-design of next generation network APIs and make them compatible with each other in some way. Okay, so this slide needs to be updated a little bit because Mellanox has been absorbed by NVIDIA, but just for legacy's sake, we have them on here. Mellanox has contributed a lot of things to, especially InfiniBand technology, that is kind of migrated into some of the near-term NVIDIA products. Then you have several labs. You have Oak Ridge National Lab and Los Alamos, among others, that design different network APIs, and they contribute to these projects that have kind of supported UCX. So there's a UCCS project that I think was hosted at Oak Ridge that contribute to a lot of the development of UCX, and also contributed to being a R&D 100 selection for kind of a useful project and community artifact. And then of course you have companies like IBM and universities like University of Houston and University of Tennessee at Knoxville that do research-oriented work with UCX. So what's so innovative? We've kind of harped on this multiple times, but part of it is that it's sort of a modular, performance portable, unified API. So what do we mean by that? I'll go into a picture here in the next slide, but really we want to have something that is low level that vendors can interact with and optimize for their hardware. But we also want to have something that is high level that users can interact with and easily design their software and applications that sit on top of. We need to do, support certain features, things like multi-threaded computing and sending data for multi-threaded applications. We also need to support new types of accelerators. So thinking about GPUs, we really need to figure out, how are we going to integrate those into our network, especially as that has become, more network oriented. Okay, so this brings us to kind of our overview of what is UCX and all the different pieces of it. We'll talk about specific parts of this today, and then there are some pieces that we'll kind of leave to the attendee to investigate in more detail. We have our application and programming models. So that's the long list of things we talked about earlier. Kind of your mVapage, your portals, your GasNet, your ARMC, OpenSHMEM. Then we have UCX provides a couple different APIs, a high-level API, a communication protocol API, and then a low-level transport API. that is closer to the hardware and that, you know, allows you to optimize for performance. Then of course you need things like you know, kind of a surface layer to sort of help set up and tear down and query your network layer, and then a memory component that allows you to register and share memory regions. So if we name those different layers, the high level layer is called UCP for protocols. The low level layer is UCT for transport. That's typically used for kind of the setup and hardware specific instantiation. So say if you're running on something like an NVLink versus an InfiniBand, you would probably write some specific you know, kind of backend that interfaces with UCT. The services module is called UCS, and then UCM is the memory component of UCX. All right, so now we bring that back all together, and we see that we have basically 4 components that, you know, make up what we call UCX. So UCP, UCT, UCS, and UCM. And then the parts on the bottom, the hardware is vendor specific, and the applications and programming models on the top are kind of the end users that are taking advantage of UCX. So there are a couple things that they always ask us to make clear. UCX is not really just a device driver. It's actually a little bit more than that. You know, it's meant to be sort of a comprehensive, you know, communication framework that has, you know, sort of useful APIs that are consistent across different technologies, while also providing, you know, that low latency access to a certain interconnect. The key thing is that you do still have to use drivers from vendors. So, you know, if you install an NVIDIA Mellanox ConnectX-6 card, you still have to go through and install the drivers, and then UCX will utilize those at the UCT or transport layer. All right. So that's kind of the high level overview of RDMA and one-sided communication and why we need UCX. I'm going to go into sort of the high level API UCP next. Before I do that, are there any additional questions? Or I guess Sissy, you can reply in the Slack if I answer your question. Okay. Okay, great. All right. So for this tutorial, what we really want to focus on is, you know, how would you probably, as an end user, you know, someone who's working on applications or programming models, how would you interact with UCX? And realistically, you're probably not going to be working with UCT because that's a very low level API. So I mentioned that the slides are all online. If you want to learn more about UCT, we do have some slides at the end of the slide deck that talks specifically about that. I think we do have a very serious disclaimer that says something like, you know, here be dragons or something like that. So be aware of that. But, you know, really we want you to focus on sort of understanding how UCP works, and that should give you a good idea of how applications use UCX. All right, so the key here is that UCP is meant to be simple for the user. Ideally, the protocol layer will do a couple different things. It'll pick the best type of network. So if you have multiple networks, say you have Ethernet and InfiniBand, and you have drivers for both of those, you would like for it to pick that. It should let you be able to use multiple interconnects. So we say multi-rail. That means, for instance, if I have 2 NICs, or maybe if I have a NIC with dual ports, you know, maybe I can use those in tandem to improve my bandwidth. You also would like for it to kind of simplify your software development. So, you know, want it to be able to kind of handle things that are not necessarily implemented for a certain platform without crashing. And then ideally, we would like for you not to run into a case where your application, you know, crashes because you ran out of, say, memory, or, you know, connection failed, or, you know, you had a packet that was too big for the interconnect that you're using. So in order to do this, there are a couple different objects, and we'll talk about how they're kind of composed together. The first is the context. An application will have one context that holds, kind of pointers to all the other objects that sit within, a UCX type connection. So this is a global context. It has, memory registrations for buffers, as well as kind of the global device context. So a good example is if you have a library that is doing both MPI and SHMIM for some reason. We don't know why, I don't have a good use case for why you would do this, but you would have a context that, maps to the MPI communication layer, and then a separate one that maps to the SHMIM communication layer. UCP worker is, kind of the engine of a data transfer that sits within a UCX connection. This is something that might be, one thread might have one worker. So say if you have multiple threads that are doing data transfer, each of these would have kind of a worker object connected with those. That kind of tracks, how data is being transferred, and then also helps with some of the setup and teardown. And then finally, we have something called a UCP endpoint. And this is sort of a connection from a local node to a remote node that, all endpoints sit underneath the UCP worker. And, all of your SYN operations are going to be performed using an endpoint. Okay, so at a high level, this is what it looks like. We have one instance per application, say an MPI type application. Then you might have multiple workers, for multiple threads. And then each worker is going to have multiple endpoints based on, the peers that it's talking to. So if you're sending data to multiple nodes, you might have multiple endpoints that map to that. There's some other objects that you need. You need a handle to a memory region. So we said when we're trying to set up an RDMA connection, we really want to set up a buffer that specifies, where we do our kind of zero copy operation with. In order to make that secure, we have a remote key handle. That's something that we kind of can transfer to remote nodes to say, okay, you can write to this memory region, and that provides some security and reliability for your transfer, that no one else is going to overwrite your data, or that you'll be able to read the appropriate data. And then there's some additional configuration information that just sets up the initial environment parameters for your UCX installation. Okay, to put all those together, so we had the context, the worker, and the endpoint, and then we've added in the configuration, which is kind of a high level, just basically a configuration object. You have sort of a memory region that says, okay, these are all the memory regions that are associated with this particular application context. And then you have R keys or remote keys that allow an endpoint to actually set up a memory buffer and transfer data to or from, a matching communication peer. So we'll dig a little bit into what the calls for these look like. Probably if you were actually interested to use this, you would have to get back and look at this in more detail. So these are just kind of informational to give you a little bit more detail. When you start up a new UCX application, and when you're using the UCP protocol layer, you first have to initialize your context. So basically you have to say, okay, I'm starting out an MPI application. I have some kind of parameters. I have that high level configuration. And then what I would like to get out is a context object. At the end of your application, you clean up that object. Basically, you release all the memory associated with that, before you end your program. And then there's some secondary helper functions, like you can get the version of the protocol layer object that you're working with. So once you've initialized your global context for your application, then you can create some workers with UCP worker create. Of course, you pass it that context again. Then you can also specify a certain thread safety mode. So you can say, either this is multi-threaded, Or, maybe I have some more restrictive thread mode where I'm saying, okay, I need to reorganize my data packets so that they appear in a buffer in the correct order. Typically an application might say, if I have a thread, I can give one worker object for each thread, and then those can kind of send and receive data independently without worry of overriding other application threads. Okay. When you create a worker, then you will end up with kind of an address of the worker object. So there's a helper function called UCP worker get address. Then you can pass that to a remote instance of the UCP implementation, and you can connect the two workers together. So that's sort of the first step before you start to create endpoints between two different nodes. Once you've exchanged that worker address, then you can start to create endpoints for the local worker, and you can specify, okay, I want for this endpoint to match with a worker on a remote node. So once you finish and set up this endpoint, then you can immediately start sending data after that. Okay, to show a little bit higher level how this might work, say here on the left-hand side, we have kind of a one-to-many type context where maybe you're trying to do an RDMA put operation to nodes B, C, and D. So in that case, A would create a context, then it creates a worker. B, C, and D create contexts and workers, and then they also set up, they get that address and exchange that out of band. So right here, if you see, we have out of band address exchange. So you can either use a UCX method or a separate method to exchange those worker addresses. Then once you've done that, then you can set up these endpoints and use those to transfer data. So putting this all together, and we're coming up to a break here, so we'll stop in a second. We have as our first example kind of how you would use UCP to implement Hello World. So we talked about, first of all, you initialize an application context, then you use something like TCP/IP to kind of set up a worker connection between two nodes. Once you have connected those workers via that out-of-band communication, then you set up your endpoints underneath the worker, and then you use something like a send receive for a tagged type send operation, an RDMA put get operation, or something like an atomic. And then finally, you kind of disconnect and clean everything up. Okay, so we're actually right on time. So right now we've come to basically a 10-minute break. So we're going to break for a little bit. When we come back, we're going to look at example 1, which is the Hello World demo. So Matt will kind of help walk us through that. But if you would like to take advantage of that, then we encourage you to go to the GitHub site. You can download the examples there, and either take a look at the code, or if you'd like to try to install UCX locally and run through 1 or 2 of those, you can do that as well. I think there's an installation script. I've tested it on a couple different platforms, but if you're trying to run it and have questions, post in the Slack here. So we'll take a break and we'll be back at 10:10, I think.
Sounds good. Thanks, Jeff.
All right, and I'm going to take a break. I'll be back.
And just to let everyone know, I think I'll keep the recording going. It'll be a little bit easier logistically to handle just one file for the tutorial.
Yeah, that makes perfect sense.
Do we have Jeff?
I am here.
Hello. I had a
Okay.
quick question. I thought you mentioned we could download the Hello World demo code on the GitHub page, but I don't actually see that.
Oh, okay. Great. I hope I named it right, but I think actually we can this is a good time to pull that up.
Yeah. Sounds good.
So let me. Okay. So hopefully everybody can see the GitHub thing here. So I mean, yes, there's I guess we should have done a tarball, which I can go back and add. But right now it's basically just is part of the repo. So if you download the repo,
Gotcha. Thank you.
just to clarify, so there's a couple things here, and I'll walk through, and then we'll let Matt kind of go through the demo. There's a script that attempts to help you kind of build UCX from source. There's also one that will, if you have enough space, will let you just install it with Conda. That's probably the ideal way to do things. But I worked on a Docker file and it didn't work out. So this is the proto Docker file. And then if you want to run, say, the hello world, you should be able to download this code and then run make. And the instructions hopefully are reasonably complete. These are kind of simple examples. But if you do want to try them, if you download them, and if you say, hey, this totally doesn't work, let me know, and we'll try to help out and update our documents here. Okay. So let me get back to my screen here. Okay, so we're coming back from break. We have a little bit of a Hello World demo, and then I'll talk about sort of the UCX memory management module, and then we'll talk about accelerators and do one or two more demos. So I'm going to hand it over to Matt. Matt, are you able to share your screen now?
We will see in a minute. I see the proper button. Can you hear me fine?
Yes.
Okay. Yes. And should be this one. All right. Can you see a screen where I just set up my environment?
Yes. If you could make your text a little bit bigger, that'd be great.
All right.
Okay. Awesome. Great.
Awesome.
Thanks.
So I'll first go over our simple Hello World application. Oh, and to demonstrate this, I'll just run it first so that you can see the output, and then explain it in VO. All right. So here we can see that's waiting for a connection. It output a bunch of UCX environment variables. That's not how a normal application behaves. We are doing that for the purposes of the demo. And so now we come out over here. And we will run our Hello World program and connect to the local host. So we get a similar output, except now we get data received, and this is the string that we got back from the server. So let's look at the code and see how it does this. Okay, so this was derived from a sample file in the UCX source codes with a lot of options stripped out and simplified. And so here we see some data structures. Mostly those are going to be useful in the callback methods. The only thing that I really want to point out is that we stash our addresses in global variables. This will be important for the endpoint creation code, and I just wanted to assure you that those are global variables and not a mistake. Okay. So down here, we get into our main function, where we do our usual C setup, command line argument, and this is where the UCX starts. So all of the UCX applications start with a UCP config read. That text at the startup, and when I ran the program, is essentially the print version. You can see it further down in the source code of what it gets from the environment. And so again, that's not a typical thing that happens. You have to specifically invoke it to do that. One status check later, and here we start setting up our UCP parameter structure. Now this structure will use a UCX theme that you'll see frequently in other similar data structures, where there's first a field mask, where you can specify which other fields in this structure are going to be present. UCX can use this both to verify that you're using a sane version of UCX and you didn't mismatch headers versus libraries, but it can also optimize features so that if there's some features that the application doesn't request, UCX can just sort of suppress and not bother with them. So in this case, we're asking for features, a request size, and a request init function. Those were the functions that I mentioned earlier, wherein those are going to be used in the callbacks to indicate completion. So feature tag, like we're doing a normal MPI program, and then tell it the size of our structure and the and a function pointer to what's going to initialize that. And then our application begins life in UCP init. Now, as Jeff mentioned earlier, this is the function that will create our UCP context, and UCP context is what owns the your memory registrations and global device contexts, things that are going to be shared across all threads. And so the config print, and then we free the memory that config was using. So now we start setting up the worker. So the worker is where the library will actually use CPU time and threads to actually progress the communication layer. So here we see our familiar mnemonic where you have worker params with a field mask telling it that we're just going to inform it about the thread mode, and then tell it that since this is a simple demo app, it's going to be single threaded and it can just operate without locks. So this is the worker create magic, where now we have a real live UCP worker that we can actually do communications with. We'll get to the endpoint in a moment, But the first thing we do with this worker is get its address structure. Now, UCX will have a magic address structure where underlying transports like InfiniBand, TCP/IP, NVLink, all that good stuff can pack our local address with all this information so that when we create an endpoint, UCX can automatically figure out the best transports to use various features. And so this local add-r lane are global functions, so comes from the global scope in this application. Doesn't have to, but we are doing silly simple things here. So this is the out-of-band address exchange function. I'm going to skip over most of it because it's just normal socket stuff. But here is where the client program, the second one that I ran, received our pure address worker address structure. And this is where the server sends it. And then it starts running the test in full. So client and server are basically the opposites of each other. So I'm just going to go over the client because that code is the best one for explaining what's going on. So we start in on creating an endpoint. You need to create an endpoint to talk to a remote worker. So the params have their field mask where all we are going to give it is a remote address structure. And that's the pure address we got from the socket. Now, there's other ways to do this. There's a lot of machinery to be able to run a TCP/IP server that can just serve up these addresses, but it's a lot of code and it's a lot of overhead. And if you have a smart address sharing mechanism like exists in HPC centers such as PMI, it's not necessary. So here we get our best case scenario where we just use the pure address to call into UCP AP create. And that endpoint is where we do our communication. So feed in the parameters, get back the server endpoint here. And so now our client will do its first send, sending its local address to the server so that the server can also stand up an endpoint. So just the mem copy the message, which is a int header and a length. And so we just mem copy our message. And so now we're setting up the send parameter structure, which is similar to the other params where you have a mask telling it which fields are going to be relevant, a callback handler. And as part of that callback handler, it'll get this context. And that's going to be how, if it's called in a non-blocking fashion, will signal that the request has completed. So here is the function that actually sends the data. We have our server endpoint, the message, how big the message is, the MPI tag. That's just another global defined above. And our parameter structure down here, which will then tell the send how to behave. So down here is where we see the UCX request machinery. Now, when you get this request back, it can be a pointer, but it can also be a error status or a success signal. And so to properly interpret it, there's some UCX macros. UCS pointer is error. And so if it's an error, in this case, we're just going to clean up our resources and exit. But if it's a pointer, which is a request, then we call into this wait function with the callback metadata, where it will just pull on that until it is completed, and then we release the request back to the library. Now, one thing you will notice is that there is no test for a UCS OK, which is the usual status message you would expect for a completed inline signal send. Now, the reason this is done is because if you get back UCS OK, then that means that everything completed inline, and this request and callback objects will never be used. So there's nothing to clean up. And we just free the message and await for a reply from the server. So the UCP tag probe function will be used to see if a particular tag has been received, where we just pass in our globally defined tags to wait for the response from the server. If we don't get anything, just try again, call progress to see if progressing the worker will get our tag, and we continue there until the break when we get a non-null tag back. And so from there, we allocate a new message based on the length indicated, and we call UCP tag message receive. So we have the worker. This is a common mix-up people have, where this is a worker object, not an endpoint object that you're calling receive on. And so the buffer for the data, how much came from the tag, this is where IO vectors and strided communications would come in, but we're just doing contiguous. The tag we want to receive, and a callback in case the handler doesn't complete immediately. By the way, trick question. We're going to get back a request here. So the familiar mnemonic, if it's a test, exit, if it's an error, exit. Otherwise, you do our wait function that just pulls on that same request object, waiting for its completion, and then free it back to the library and inform the user that the message was received, which is what we saw in our the earlier output. And so print the message, and then we have our cleanup code where the only UCX bit here is destroying the server endpoint. So here's the server. It's just the same thing as the client, except in reverse, where it gets the endpoint, sends the message, completes, destroys. All right, I think I have finished on time.
Yeah, I think pretty close, Matt. I guess one quick question, and I'll pause if anybody has any other questions. So you mentioned this example has the TCP/IP out of bounds address exchange.
Yes.
But you're saying if you had something like PMI, you wouldn't necessarily need that piece. Like if your application used PMI plus UCX.
Correct, because PMI has a global all-to-all where you can stuff an address structure, and then you get back what looks suspiciously a lot like MPI ranks full of address objects.
Mm-hmm. Got it. Okay. Great. Well, thanks, Matt.
Mm-hmm.
All right. I guess, are there any other questions? If so, please post in the Slack. So we had one question, I think, from David. He said, when building UCX, do we recommend using master branch or release? My answer was I use 1.13, just because that's kind of the latest stable, and there is a lot of interesting development that happens in the master branch. I mean, I'm sure with testing and UCX has CI/CD, it's probably safe to use the master as well. So this is production level framework,
Right.
as opposed to research code. So
Yeah, and I assume the .x branches are also fairly stable, and maybe you get some more.
yes, yeah, those
a little more
are
bleeding edge.
yeah, kind of patch
Great.
level, and I don't know if I can specifically tell you all the features for each of them, but that
Sure.
might be Yossi or somebody could maybe elucidate if you have questions.
Yeah, newer release branches will always have better bug fixes, but
Right.
masters should be fairly safe.
Okay, well, let's see. So I'm gonna steal the screen back from you, Matt. Thank you very much. If you have questions about the demo or the code, feel free to post in the Slack. So, and then again, this is the examples UCX Hello World. So, so we kind of went through the Hello World demo, and just to remind you, so Matt kind of walked us through you set up the client and server, you do that initialization. He showed an example where you use TCP/IP to basically create your UCX worker object, then you exchange the address data for those using TCP/IP, and then once that is kind of the two endpoints are connected, then you can set up your local and remote endpoints. So what I'm going to talk about next is basically the memory management piece of things. So this still lives within UCP. So these are still things that you would use in your application, but here basically you're creating buffers and using those to do different types of operations. So send, receive, input, get, and atomic type operations. So I'm going to quickly run you through some of the API calls. Again, these are things that, hopefully these slides are a good reference. Obviously we don't remember all these by heart. I mean, Matt might, but the rest of us don't. But basically just to give you an idea of sort of the steps that you would use to use UCP in an application. First of all, this assumes that we've set up our context, our worker, and our endpoint. And then we talked about these remote keys. So now we're starting to set up memory buffers that we actually use to specify user specified memory region, and that's what we're using to do kind of a zero copy operation between two different nodes. Here we have UCP mem map. Again, you have your context, you have an address that your application can use, but it also points to some kind of buffer, size, flags, and then some kind of UCP specific handle. At the end of your application, you really should be running UCP mem unmap for obvious reasons, but we won't talk too much about that. Okay, so to actually send data, to remote regions, if you remember, we had the remote keys, and so one way to exchange the remote keys is we can create an RKey buffer, and we do that with this function UCP RKey pack. Again, that takes a context, that takes a handle to the memory region that we've created, and then it specifies some array of R keys that you might be wanting to share with another kind of trusted destination. On the other end of your connection, you pack all these R keys into a buffer, then you send that to a remote node, and then it'll run unpack, and then it'll use that to kind of complete the connection from the sender to the destination endpoint. Okay, so at a very high level, you create a memory buffer, use keys to kind of securely connect to endpoints. Now we'll talk a little bit about the different types of operations you can implement with UCP. Typically, we're looking at things like applications like MPI and a PGAS, partition global address space, type language. Here we put OpenSHMEM, but it could be something else, like UCP. There are different types of operations. MPI supports kind of a symmetric send receive. It also supports a one-sided put get / atomic type operation. PGAS, just supports one-sided communication. So it's really just going to support a put and get type operation. So we'll start with UCP put non-blocking. And as you'll notice here, there are quite a good number of parameters for these. There's specific operation parameters. So we have at the end here, we have UCP request param. Our first field is basically our endpoint handle. So, what is the connection between, say, node A and node B? How much data are you sending? Basically your buffer size, the remote address that you specify by setting up those memory buffers, and then the key that you need to actually, do that put type operation. Similarly, get looks pretty much the same. You're just gonna, your parameters are slightly different. You have your buffer, your count, and your remote address. So you're trying to read some data from memory B back into memory A, but the parameters are very similar. Again, this is a non-blocking get operation. You can also do things like tag sends, where you can specify certain tags, and that's used for ordering. So if you're sending a large amount of data, or if you're sending chunks of data, say you have one big buffer that you need to packetize and send efficiently over a high-speed network, you might want that data to be reassembled on the receiver side in a certain fashion. To do that, use tags. And so, you have an extra field for the message tag here, UCP tag T tag. And then on the bottom, we just see what that looks like. You might say, okay, I send buffer 1, 2, and 3, and they might arrive at the receiver in slightly different ordering, based on the, if you're doing things like if you have multiple paths to the destination, for instance. But, once they get to the receiver, you want to kind of reassemble them in the buffer in the correct order. So something like a send tag send is a good way to do that. Same thing with receive. The only addition that you'll notice here, if you kind of switch between these two, you'll notice that you have buffer count tag and parameters. Here you have buffer count tag and a tag mask. So this is basically, what part of the what part of the incoming message should you use to match up tags and see, okay, how do I determine that I've received all the appropriate data? So very similar again. You'll notice in a lot of these different calls that we have for send and put and get, that the return operation is a UCS status pointer. So we mentioned there's UCP, UCT, there's UCS, this kind of module that sits sort of to the side, and UCM for memory. But this UCS status pointer is basically, how you determine if, say, something like a send operation completed. Okay. One thing you'll notice if you do like a put or get non-blocking, you may not get any information back. So those are, those are things that are typically one-sided. You sort of assume that they completed correctly, and the application has to handle that if they did not. So other different sort of request handling things, basically you can say, is my request completed? Am I done with a certain request? And kind of set up and tear down type routines. Okay. So we have some variations of some of the other types of send operations. Here we have a send synchronous non-blocking. Again, that has a very similar syntax to the tag send non-blocking, but I think it's just a synchronous variation of the tag send. Okay, So one interesting thing, if you think about one-sided communication, you can actually do atomic operations. I mentioned things like swap or compare and swap, fetch and add. These are all kind of traditional things where you have a very small data value that you want to very quickly replace some remote data with. So, typically you're doing some kind of put type operation. You're passing a piece of data and you're saying, I want you to compare the two values, and maybe I want to swap with the value that I sent. UCP supports that. The UCP atomic op non-blocking again. Here you're specifying an endpoint, and then you're specifying an atomic operation. So there are different types of atomics that are defined in the UCP spec. And then again, you have things like your buffer, your count, your remote memory address, so your pointer to the data, and the remote key that you need to access that remote memory buffer. Okay. So just to wrap back around, we talked a little bit about initialization, bootstrap, sort of setting up endpoints. These previous commands that we just talked about, all these things, like tag syn, non-blocking, the put operation. These are all things that are within sort of our connect phase of the application. So if you go back and look at the hello world, if you just want to look at the code, if you don't have time to run it, it might be useful to look and say, okay, where do these commands actually fit into the communication flow? So they're all things that are implemented in this high level UCP layer, but there's sort of different phases of the application. Okay. All right. Okay, so now I'm going to hand it over to Oscar. I'm going to keep the screen share, but he's going to talk a little bit about some of the accelerator support and UCX API, and then I think we'll have at least one more demo before the break, and then if we have time, we might cover the other demo, I think, a little bit later. Okay, so Oscar.
Thank you. So just a reminder that a UCX also supports accelerators, and this particularly GPUs. UCX was designed from the beginning with accelerator in mind, as accelerators are structured as transports. So basically, the transport abstraction is responsible for transferring the data between the host and the accelerator memory, or between the accelerator to accelerator. Protocols are agnostics of the types of accelerators, and basically no need to change at the higher level logic to add the new accelerators. Communicating accelerators memory works the same as passing a host memory. So that's that abstraction that is provided to the user, and just as passing a pointer to the accelerator memory in the UCX API, just as we do that, can be done that way. There is, when you implement things at the programming model level, or basically as a use of the UCX, there is no need to change anything to deal with the accelerator logic. That's already implemented as part of UCX. Next slide. So in addition to supporting accelerators, UCX provides also, we have also Python bindings for UCX, and they are currently, in addition to the Python, we also have a Java bindings and Go bindings. And the idea is that these bindings can help when we started to use UCX on a beyond HPC applications, basically, so that you can be support frameworks for data science, AI, and big data. The Python bindings, UCX has its own bindings, as well as there is a Rapids bindings that have UCX API, and the Java bindings are already available in UCX, as well as the Go bindings. So this is important because UCX is being used in different frameworks for data science and big data. And most of these AI frameworks and so on use Python, and Rapids is basically one example of those frameworks that use that can use UCX through Dask. And yeah, and one of the interesting capabilities is that these frameworks use the client server model to basically to establish connections between the endpoints, and this is also being done through the Python bindings, and as well as when they do transfer to communication, it can be used basically in an efficient RDMA. Next slide. And so this is for math.
Yeah, I think we kind of put the two demos here together. Let me see if we have one more slide, or if we should go ahead and jump to that demo. Yeah. So I don't know, Matt, do you want to run through the CUDA demo quickly? We have about 10 minutes here, or we can walk through the code for that if you want.
I can actually do the demo
Okay.
fairly quickly. Let me get my allocation back.
Okay. So you know, the reason that we're bringing up this, so this is example 2 basically, but the reason we put this in here is just to show you that if you want to use ECP, you can also integrate it with CUDA, so you can use, you know, CUDA registered memory to run UCX on 2 GPU instances. So this example is similar to the first one, but it is, you know, basically just using CUDA. So that's also why we included the Conda install, because if you're actually using this with the GPU system, then, you know, it's hopefully you already have CUDA installed, but if not, the Conda install kind of takes care of that for you. So okay. All right. I will stop my share. If I can find my little pointer here.
I took it.
Okay, great.
But yeah. So we can do the same thing with this. Where we have our GPU example. And so we can do the same thing we did last time, where we start up the UCP worker. And then we connect to the local host. And we get, by and large, the exact same output. Now, rather than walk through the entire code base again, I just want to show a diff. Because remember, part of the point is that you can by and large use the same code. And so changes by and large are just adding CUDA. There's the header files, function wrapper. The C's mem copy gets replaced with the CUDA mem copy. And so far, it's all just CUDA changes. Our CUDA changes, changing how the test string is generated. More malloc functions. And so here is where we see our first UCX change, where send parameters gets a memory type field and a UCS memory type CUDA. Nothing else in this entire code from the UCX API changed. We're at the end of the patch, and as you can see, CUDA free is where it ends, and so there was no changes to the client code either. We're just in the UCP server. To help reinforce that, just pull up the code itself. All right, here's the client. So that's the wire up. And so you'll see that our tag receive function just didn't change. We malloc some CUDA memory into MSG and called the exact same function with the exact same parameters. And then this just loads the data onto the GPU. And so then copy out for printing, and this is it. This is what changed.
Nice.
Mm-hmm.
So quick question tying back to one of our earlier questions. If somebody ran this, say, on like a DGX system, presumably it would kind of pick whether to use NVLink or PCI Express without you actually needing to specify anything. So, okay, awesome. Well, thank you, Matt. So, we don't have any GPUs to hand out to everyone, but if you have a GPU cluster, if you want to check this example out, and test it out, then it should run it should look exactly like the first one, and that's on purpose. So, all right, I'm gonna steal the screen back from you.
All righty.
Let's see if there's any questions in the chat real quick. So Peter has two questions. Or actually, there are a couple of questions. So David says, would this example work with a normal CUDA malloc as opposed to a CUDA malloc managed?
Were you saying something?
Sorry, no, just tongue twister.
Okay. But
so
yeah,
the question is, would we use CUDA malloc managed? Would this also work for CUDA malloc?
I believe it should. I just wanted to also given the type hints and make sure that this example was as bomb-proof as possible.
Yeah. So in theory, yes.
Do we have Yossi on the line? He'd know better.
Yes, I'm here.
Right. So is this supposed to work with a normal CUDA malloc in addition to the CUDA managed memory?
Yes, it works with any kind of CUDA memory that you allocated using standard CUDA APIs. You could pass it to UCP communication functions. UCP would recognize that memory. It can actually distinguish also between managed memory and pinned memory and do the right thing for it.
Nice. Okay.
Very good. Thank you.
Awesome. There's one other question from Peter that says, can UCX infer that the memory comes from CUDA, or does the application level need to set that kind of UCS memory type CUDA flag in all cases?
So actually, both are possible. UCX, if the memory type is not specified explicitly, and then UCX would try to detect the memory type in any case to distinguish between a CUDA memory or host memory. because you cannot really access CUDA memory from things like memcopy. It would lead to segmentation fault. But this thing can take some time because it's either lookup in a memory type cache, which is a data structure lookup, or if it's not possible, it would call things like CUDA APIs to detect the memory type. But if the application is already aware of the memory type upfront, it can save the time by providing a memory type hint to the communication functions.
Okay, great. All right, let's see. And then I think there's one more question that says, can you use CUDA malloc manage for put get operations?
Yes, it's possible. So all the combinations are supported, but it's not the performance of that can vary according to the memory type.
Okay.
So sometimes if it's not possible, for example, to use the RDMA to target CUDA managed memory, it would fall back to software-based protocols.
Got it. Okay. Sounds good. All right. Thanks, Yossi, and thank you, Matt. So let's see. I'm gonna jump back and steal the screen here. So I saw we have one more question. I'll jump to that in just a second. Since we're coming up on our next break, I'll just talk through the UCX Pi briefly, and then we'll, if we have time, I think we'll come back to it in the next session. So we may kind of move the actual demo for that sort of to the end of the session 3. But we have one more example, which is UCX Pi based, and it's example 3 in our repo. And kind of the key thing here is that we have sort of 2 different implementations of using the Python interface for UCX. So we have a version that is specified that is kind of the rapid style of using UCX Pi. So this is something implemented with NVIDIA Rapids, and that requires the use of this asynchronous library. So here you'll see some things like async def send receive, and then some things like await client send. So you have this additional dependency of using the asynchronous IO library. On the right hand side, we have what looks to be a little bit longer code segment, but I think that's a little bit misleading. We didn't have a really good match for the code. I'll see if I can go back and clean that up. But one thing to take away here is if you look at sort of the code that's being implemented, then you have things like UCX API, UCX endpoint, create from worker address. So that's where you're creating an endpoint. You have the worker that's set up, and then we talked about things like the UCP tag send NBX. The send request uses an API called UCX API dot tag send NB. So on the right hand side, this looks a lot more like the kind of traditional C UCP style interface. And it's my understanding, I think from Matt, that this is probably the way that UCX Python support will go. It'll be more like the right hand example than the left one, just because it's a little easier to work with as a user. Okay. So that's example 3. We'll revisit that. We did have one more question. I think Hessam asked in the last example. He said we're linking with UCT and UCS, and he says that really necessary since we're mostly using UCP.
So I actually decided to rebuild the applications just to test this out. And it looks like it does fine without UCT, but you need UCS. But honestly, I'd just not worry about it and leave them all in.
Yeah, that's a good point, Matt. So I think to answer your question, you probably don't need the UCT library because we're not calling any of the functions explicitly from UCT. But and I have to look exactly at the code, but it is using like a UCS status T object is returning that from some of the like send or put operations. So you probably do need the UCS library. Okay, great. Thanks for all the great questions. So right now we're at our second break. We're at 11 Pacific time. And as I mentioned, we had a UCX API demo. We'll kind of move that towards the end of the next segment. So if we finish a little bit early, then I may ask Matt to jump back into that. But we're going to take a short break, and then we'll come back in about 9 minutes, and Chris will tell us about what's new with RISC-V support for UCX.
Sounds good. See you soon.
Thank you.
Can't go far in 8 minutes. So Okay, I have it as 10:10 here. So our next kind of segment is sort of new stuff and advanced topics. So we'll have Chris Taylor of TCL is going to tell us about RISC-V support for UCX. Chris, are you okay with sharing slides, or do you want me to drive?
If you don't mind driving, I'd appreciate it.
Okay, great. All right.
Less opportunity for technical issues.
Totally understood.
Hello, everyone. I'm Chris Taylor. I'm with Technical Computing Labs. I'm a senior research scientist. Today I'll be speaking about RISC-V 64-bit support for UCX. So bottom line up front, UCX now runs on a RISC-V 64 board. The PR is 8246, adding support for RISC-V architecture, RV64G. I'll explain what RV64G means in a minute. This implementation or this port runs on Sci-5 unmatched boards. We have a cluster with ConnectX-3 and 4 RDMA devices. We were able to successfully get OpenMPI and UCX's OpenSHMEM implementation working and verified over Ethernet and IP over IB. This is run on Ubuntu and Slurm. And before we get into versions of Ubuntu, there's only one version of Ubuntu that runs on RISC-V currently. So that kind of should orient you to a single solution. Verb's IB support is blocked on RISC-V. Canonical has announced that Ubuntu should have this issue, have an underlying issue with 32-bit support and a 64-bit kernel resolved this fall in stable. So because Verb's IB requires 32-bit compatibility in the 64-bit kernel, we're currently not able to get Verbs running, and that's all right. Next slide. So for those of you who don't know what RISC-V is, it's a free instruction set architecture. This means that if you're a hardware engineer and you want to make a processor, you can go take the RISC-V instruction set architecture and roll your own RISC-V chip without paying royalty fees or any other kind of service support fees to the RISC-V Foundation. RISC-V has a core suite of extensions. So G is a letter that means like a suite of extensions for the instruction set are supported. It's like floating point, those kinds of things. So when I say RV64G, I mean RISC-V 64-bit and G, which is the suite of instructions that go along with that. Other extensions for RISC-V involve caches, vector units, and virtualization. And if you think about it, right, the extensions act as building blocks for composing a processor. Right now, RISC-V is very popular in Internet of Things space, and my company is interested in trying to move RISC-V into the HPC space. Next slide. So you get 32-bit instructions on RISC-V, and in the context of a 64-bit environment, that means you get to load 64 bits of data using 32-bit instructions. So you get an LUI, which is a load upper immediate instruction, and that'll load the upper 20 bits of data into a register. You can use an add-I after that to load 12 bits of an immediate value. So with those two, with the 20 and the 12, you get 32 bits. So it takes like 2 instructions to load 32-bit value. 64-bit values take about 4 instructions. The RISC-V automatically sign extends immediate values. So if I have like the integer 1, and let's say that gets on the borderline of the 20th bit or the 12th bit, the machine will automatically flip sign extend that immediate value. This means you have to kind of take some care when you're dealing with immediate values. There are 16-bit compressed instructions in the instruction set architecture. It has a weak memory consistency model, so data instruction caches can be explicitly flushed and should be in special cases, particularly in the context of UCX. This creates an opportunity for performance optimizations. The base instruction set architecture has 32 64-bit integers. If we're talking about RISC-V 32, we have 32-bit integer registers. The floating point extension provides 32 64-bit floating point registers, and you get 16-byte stack frames like you do in most languages. Next slide. UCX implementation notes. UCX requires self-modifying code which is to instrument, I think it's like 8 memory system calls. So malloc, mmap, all those things are instrumented by UCX. And it turns out that there is, at least insofar as RISC-V is concerned, a sufficient amount of memory in each of these memory system calls that are instrumented to insert the appropriate amount of the appropriate redirection code. We attempted to use ELF relocation. It turns out ELF relocation is in progress in RISC-V. There's some bugs that have to kind of get worked out. Hopefully we'll get there pretty soon. Program counter relative jumps are a little tricky. You can't directly modify the program counter, so you have to kind of go through instructions that will modify the program counter and then present you with a result in a separate register. So as an example, to do redirection, the standard or the specification RISC-V encourages using the AUIPC instruction followed by a JALR. The first one, the AUIPC adds an immediate value to a program counter and then presents the results into a register, and the jump and link register instruction will perform the jump, right? Now, we attempted to use this technique because it's what the specification encouraged us to do. Turns out it had a lot of issues, particularly with return addresses on the call stack getting wiped. So we jump, run the code that's self-instrumented, then come back to perform the rest of the malloc, and then we get a segmentation fault or we get some kind of terrible result. In order to get around this issue, we ended up using the add immediate instruction, and then a jump and link instruction. And of course, they had to apply some special care due to automatic sign extensions. Next slide. Because UCX requires self-modifying code, UCX uses a constructor attribute, which means that all of this instrumentation happens before your application even runs. This is part of the wiring up process, probing the hardware to make sure it has the appropriate hardware acceleration components. So you can do InfiniBand type operations, or it'll fall back on the appropriate Ethernet software variation. There are some memory consistency issues in RISC-V. Currently, you can only flush instruction caches. You cannot flush data caches with the RV64G extension because those are supervised instructions. So when you call the GCC intrinsic built-in clear cache, it's actually just calling RISC-V flush iCache, where iCache is the instruction cache. POSIX cache flushes are not supported in Ubuntu's RISC-V. So if you type in man page or man cache flush, that's a POSIX function that'll flush caches for you. That's not implemented and not supported currently. Next slide. So long-term solutions to some of these problems, there is a CMO extension. This provides cache flush operations for data caches and instruction caches that go far beyond what comes in RV64G. This is going to fix a lot of these issues we kind of hit with our implementation or our port of UCX to RISC-V. My organization, my company, is going to make a concerted effort to make sure CMO is a requirement for HPC-oriented RISC-V processors. We filed reports upstream about some of these issues we've discovered in the glibc space, Clang libc, GCC Clang, and then the GNU Linux kernel folks. Takeaway here, UCX works on RISC-V for Ethernet and IP over IB. Future hardware extensions for RISC-V and OS support will bring full functionality. And that's it. Just to kind of clarify, we have a patch submitted. We're in the process of getting that patch polished and ready for inclusion into RISC-V. There's some implementation choices that we made due to the sort of experimental nature of the hardware that we kind of have to get cleaned up and sorted out before it gets formally added in. But you can pull this patch from GitHub and use it on your sci-fi hardware at home.
Okay, great, Chris. Are there any questions in the Slack? I don't see any at the moment, but feel free to post questions. I think Chris will be here for a little bit. I guess I had one question for you, which is
Sure.
If we, so you guys are using Sci-Fi Unmatched, which is this, for everybody who may not know, is a RISC-V motherboard and CPU combo. But they've stopped making that. Is there anything that you can buy now to actually test this on? Are we waiting for new hardware to do?
So we did the implementation on the Sci-Fi boards, and you are correct, they're currently not available. The Sci-Fi folks have more boards coming out soon. You can go out and buy RISC-V boards that we believe will run this code. It'll require you to make sure that those boards support RV64G. So that board, if you think about, a box of cereal, it's sort of the ingredient list on the side of the box, right? When you go get that RISC-V hardware, be sure you see somewhere in the notes around the hardware that it supports RV64G. And if that's the case, then you should be fine. And it'll definitely work on Ethernet, just plain old, standard commodity Ethernet.
Okay.
That's a great question. Thank you.
Well, inquiring minds want to know. So I only have one.
And if it breaks, then post a bug and we'll do what we can to get it fixed.
Yeah, I speaking from experience, I have one board, so this is really cool, but I'm unsure. I have to find another board to talk to from that for that one Sci-Fi board that we have. So
yeah. Thank you very much.
Awesome. Okay, thanks, Chris. And I see. Let's see. I think maybe somebody typing a question. Let's see. So our next speaker is. I'll go ahead and jump to the agenda again. So we have kind of one more big topic, which is kind of our advanced. We're saying advanced implementation. Okay. Thank you, Peter. Peter says he doesn't have a question, but he says this is a cool, unexpected update. So, and that's kind of why we included it here, is we were. One of the focuses of this tutorial is that UCX is meant to be sort of useful on all types of platforms. So I think that's why we're really happy that we were able to have Chris and feature his work here. Okay, so we have one more segment, and then if we have time, we'll come back, and we have one or two questions I think we haven't gotten to. So we'll loop back to those. But next up, we'll have Yossi is going to talk about some of the quote unquote, we say advanced, it's not super advanced, but it's still a little bit lower level, kind of UCX bindings, which I think we already talked about some of those with Python, but more specifically talk about the OpenMPI integration. Yossi, do you want me to drive the slides, or?
Yes, please.
Okay. All right.
Okay, so hi everyone. This part is about how we integrated UCX into OpenMPI. So overall, the integration is quite simple. It's in most cases it's a pretty straightforward translation from MPI API, or more specifically the PML component inside OpenMPI to UCX API. But still, it can demonstrate usage of UCX in a real life use case, and yes, everyone here are familiar with MPI, so yeah, could show how UCX fits into that model. So in order to run OpenMPI with UCX, we use a component called PML, or a point-to-point messaging layer, implemented over UCX transport. We can set different parameters like a verbosity level or a priority to make sure it's enabled. But the basic command line to run it is shown here. We can specify MCL, PML, UCX to specify the right component. Optionally, we can also set a UCX environment variable to specify which network devices to use on the system. By default, UCX would try to use all available network devices that have high-speed ports. But if we want to restrict it, it's possible to do it by a UCX environment variable. And there are many, many more UCX tuning parameters that can be applied. Most of them are intended for very specific cases or for debug purposes. Some of them are documented in our read the docs page. But really the basic parameters that we expect people to use is the net devices. Okay, next slide. So yeah, so UCX would select the best transport to use among the available low-level transports, which include for RDMA, they include the UD, RC, and DC transport, both over standard verbs and accelerated verbs in the RDMA core library, shared memory, if we have intra-node communication, and UGNI if it's available. OpenMPI uses full or direct modems. This is a typo. It means in OpenMPI terminology that we can either exchange all the endpoint addresses in the beginning of the job, which can take some time to initialize, or we can do it in a lazy fashion, which means that only on the first time some send operation is being made to a destination, only then we would go and fetch that endpoint address from the modems. And there is a cutoff parameter, so we can specify that some amount of ranks would be exchanged initially, and the rest would be on demand. And after exchanging the address, UCX would connect the ranks by creating UCP endpoints for them. Next slide, please. So just to recap on the object that we have to show how they map to OpenMPI. We have the UCP context, which is a high-level application context. It has one instance for the OpenMPI PML component, which is also called the PML UCX module. Worker is an instance of a communication thread. We also use one of that in OpenMPI, at least in the basic implementation. And endpoint is a connection to a remote worker, and it's embedded in OpenMPI OMP-proc structure, which represents a process or remote process actually from the point of view of OpenMPI. Next slide. Memory, RKey, and UCP config are additional objects. So UCP mem is a handle for registered memory, and RKey is a handle to a remote registered memory. These objects are used for the shmem part of OpenMPI, which we will not describe fully here. But they are used to register the shared memory heap, and they have actually a map of segments, of remote segments, to the shared memory heaps of other processes in the job. And the UCP config T represents a configuration object. It can be used to read, modify, and set values for UCP configuration parameters. And next, please. So if we look like on the overall layer structure, on top we have the MPI application running on top of the OpenMPI library. That's a thin layer in most cases on top of a PML UCX component. And that in turn is also a thin layer on top of a UCX library, which does all the heavy lifting of the communication. So if we look at it, there's one or two function calls in OpenMPI that translate from an application layer down to a UCX. Next slide. Yeah, so during the initialization part that is driven by application calling MPI init, there is internal function OpenMPI, which is called the OMP-MPI init. That function opens and initializes everything, including all communication components, which in turn includes the PML UCX component. And in the PML UCX initialization callback, we read the UCP configuration, call UCP init, which creates a new UCP context object, and then release the configuration. Next slide. In addition to creating the context, we also create a single worker object that is also being used as a context for all the tag matching operations. So the way we map communicator rank and tag and user tag to UCP tag is we pack all of those to a 64-bit UCP tag, and we don't really distinguish between tag matching queues of different communicators. And we can do that because UCX maintains a hash table for matching queues, so it would be scalable and not just put everything into a single list. So wait a second, go back. Yeah, so after we created the worker, we get the worker address. The worker address is actually a combination of the network addresses such as lead or IP address and the object-specific address such as QP number or TCP port number. And we query all of those from the worker. It packs all the addresses of the low-level transports into a single binary object that we publish into the mechanism that is called the MODEX. And after we do that, other ranks or other processes in the MPI job can access this binary address and create a new UCP endpoint to it, which essentially creates UCP endpoint to our worker. Next, please. Yeah, and if we look at what happens during progress, so in OpenMPI, you can register a progress callback that is added to the loop and to the list of progress functions that is being called in every MPI blocking routine. And part of that is calling UCP worker progress, which will really progress all communications on our single UCP worker, including pulling completion queues, progressing tag matching, progressing rendezvous protocols, and so on. Next. So now we'll have a quick review of the send and receive flow. So MPI iSend, which is like an example of a non-blocking send operation. There are many variants to it, but eventually there are actually several variants to it, but eventually they all map to a UCP tag send and B. So MPI iSend is being translated into the PML layer by calling the callback PML UCX iSend. If we're using a partial MODEX and we want to create endpoint on demand, we also call a MPI PML UCX add proc, which would create a new endpoint if it's not exist yet. After it's being done, we can go ahead and call UCP tag send B on the endpoint. That actually packs the user tag, including communication ID, rank ID, and of course the payload into a buffer. And then it's inside UCX, it's being translated into one of three functions. It can take either the short protocol, vcopy protocol, or zcopy protocol, and each of them is optimal for a different message size. And the exact thresholds are being tuned at runtime, depending on the configuration of the hardware, the available transport, and so on. So for example, not all transport support short, or in some cases, if the transport is very slow, it would make sense to use vcopy, because like adding memcopy overhead would not be a significant impact on the performance. But if we have a very fast transport, it would make sense to switch to zero copy at earlier stage, because relative to the potential bandwidth that we can achieve, memcopy would be a significant overhead. Okay, next. So after we initially posted the send operation, there are three things that could happen. First thing is that the operation could be completed immediately. That could happen with a short or vcopy protocol if we were able to inject the message into the transport, or if we copied the user buffer into internal bounds buffer of UCX. There's no need for the user to do anything else. From the user point of view, the send buffer can be reused, and it's being posted into UCX. And in this case, the tag send function would just return null, and no resource or request or anything like that would be allocated. So UCX has a kind of a dummy send request that is always completed, and that request is going to be returned from the MPI ISEN function. Another option is that we could post the operation, but it's not completed yet. For example, with a 0 copy, we posted it to the transport, but it's not completed because it's in the hardware ownership right now, but the hardware cannot release it before it's really been acknowledged by the remote side. So in this case, a request handle would be returned. That would be wrapped in the OpenMPI request. Actually, OpenMPI request is a substructure of the UCP request, so we don't have any additional memory allocation here. And after the request is really completed, the callback function, which maps to an OpenMPI callback function, is invoked. That callback function marks the request as completed. There is a special field in OpenMPI request that indicates the request status. And after that, any kind of MPI wait or send routine is able to recognize that that request is completed and return the correct status to the user. So in terms of data types, all data types that OpenMPI has are supported. Contiguous data types are the most efficient because we can just translate them to a buffer and length. But if the data type is not contiguous, we are using the OPAL converter to first pack the data into a contiguous buffer. And then we use something in UCP called the stream data type. That is the purpose of that is to be able to pack data types directly into UCX DMA buffers and not use any intermediate buffer allocated on the MPI layer. Please go ahead. Yeah. Okay, so for the receive flow, it's very, very similar to the send flow, with minor exception that the receive is being done on the worker, because the worker is our tag matching context and holds all the tag matching queues. So that's why we post any receive operations on that. And in MPI, we can have expected receive or unexpected receive. So if it's expected, we just post it to the worker and wait for the right message to arrive. If it's unexpected, we can pull it out of the incoming messages queue and complete the receive request and return it back to the user as completed. So in each of those cases, regardless of it being expected or not, it can go through a eager protocol or rendezvous protocol that is actually decided by the sender, but the receiver, when it detects that some message has arrived, if it's eager, it would be copied to the user buffer. And if it's rendezvous, the receiver would progress the rendezvous protocol, which in most cases means send the RDMA read operation or something equivalent, pull the data from the sender and send acknowledgement back. Yeah, next. So except the simple receive function, MPI also MPI specification also has a probe and the message probe functions. So in PML UCX, we implemented using a UCP tag probe and tag MSG probe, respectively. So the second one can provide a pointer to the incoming message in case something really arrived. And that is encapsulated in the message handle. And then it could be used later on by a MPI mReceive function. So if we look at the overall flow, after we post a send or receive operation, some things can happen during the progress, especially if things are not completed immediately. So UCP worker progress would call UCT worker progress. The UCT worker is actually a list of all callback functions on all the transports that actually need progress. And the list is being changed dynamically to avoid calling callbacks which do not do anything, because even calling a function every time is a significant overhead. So the UCT would progress all the transports and make sure that things are being sent or received and completed as needed. And also all the callbacks that the user specifies over on top of UCP layer could be called only from a UCP worker progress context. A callback cannot be called from any other UCX function. And that provides a safety guarantee that a callback can call any kind of UCP API except the UCP worker progress. Okay, and finally, when we finish the job, we call MPI finalize, which translates eventually to PML UCX del procs. The del procs function is destroying all the UCP endpoints. It's doing it in a batch because the UCP destroy can potentially wait for some kind of acknowledgement from the remote side. And after all the UCP endpoints are destroyed, then there is a barrier over a PMI, and then the worker itself is destroyed. Okay, next. And after the worker is destroyed, the context is destroyed, and at this point, we're done. Okay, next. Okay, so like in high-level overview, it's pretty simple to build OpenMPI with UCX. You just do the regular process of building UCX, install it into some specific place. Then you would build the OpenMPI and just specify with UCX, with a path to the UCX installation directory. And OpenShmem, which is a reference Shmem implementation, works pretty much the same way. You can provide a UCX installation directory, and then it would use it.
Okay, thank you, Yossi. I actually have, I think now is a good time to revisit. We have two questions in the Slack that one of which I think is relevant to what you just talked about with the OpenMPI implementation of on top of UCX. So I think David asks, basically the examples that we've talked about today have been mostly manual non-blocking probe progress models. And he said, are there other progress options for UCX that are a bit more automatic? Do users have control over progress alternatives for a given transport?
Yeah, that's a great question. We get this question once in a while. So the current model is that the progress is always driven by the user. And the reason for that is that eventually UCX is a user space communication library. And for most of the transports, including shared memory, RDMA, and even TCP to some extent, some of the progress has to happen at user space. So the goal is with a user-defined progress, by explicitly calling UCP worker progress, is to let the application have a full control over the progress model and not do things implicitly that could create unexpected performance or unexpected behavior, or even like stalls or deadlocks. And so if an application or some use case needs asynchronous progress, the recommendation would be that the application would spawn a thread that would call UCP progress. I mean, UCX could do the same thing. It could spawn a thread and do the same progress internally, but that would just be that could create unexpected performance issues, and we prefer to not do things like that under the hood.
Okay, great.
That makes sense. Yeah, thank you.
Let's see, jumping back up, this was asked a little while ago, but I figured when you were speaking, so I think Peter asked, he said said that the MR cache moved to the UCP layer, and he was wondering what was the reason for that, and if there's any impact for the end user.
So not sure I understand the question.
This was from one of the, I think this was from the what's new in UCX.
Moving into UCP layer. Yeah.
Yeah. Let me.
There are a few reasons for doing that. The simplest one to explain is that CPU overhead, because if we do it on UCT layer, you have to go and call some callback or some indirect function to the UCT layer in order to register memory. Even if this function call eventually goes to data structure lookup, if that lookup was inlined, like we could do it now when it's on the UCP layer, we can remove some of the software overhead. We can assume that this data structure is protected by the UCP context lock, or at least has the same thread safety scope. So we can eliminate some of the locks for the registration cache. And combining those two things is able to reduce some of the software overhead for registering memory. So it used to be like a few hundred nanoseconds just to look up something in the registration cache. And now it should be like less than 100 nanoseconds or even less.
Okay.
And the second reason was to support a DMA buff. And the reason is that we want to query the DMA buff file descriptor only the first time we register some memory. But we're not able to do that if the fact that memory is registered the first time or not is hidden by the UCT layer.
Okay. I think Peter also asked a follow-up, which is can you use the registration cache when you're statically linking? So that was another new feature that those introduced recently.
Yes, those things are unrelated. And,
okay, gotcha. Okay, great. All right. Thanks, Yossi. So if anyone else has other questions, or Peter, anyone, if you have follow-up questions, definitely post in the chat. So thank you very much. I think we're slightly ahead of schedule, although I think we sort of shifted some things around. So what I was going to do now is we're kind of at the summary part of our presentation, and definitely if you have more questions, now is a great time to ask them, or if you want to go through specific examples in more detail. What I was thinking too, if Matt's available, if he wants to walk us through the UCX Pi example, we do have a little bit of time to do that. We kind of moved that just so we didn't get too far off the listed agenda. But Matt, are you available?
Yes.
Okay.
Need a moment to reestablish the environment.
We should have just told you to stay logged in for 4 hours. Okay, great. And I think I've tried to respond to everybody's questions in chat, but if we miss something, definitely feel free to ping us.
Do you mind if I ask a question verbally?
Yeah, go ahead.
I'm curious about collective operations. I believe I know of a project called UCC, right? Unified Collective Communications. Is that
Yes.
affiliated with UCX? And or is the team involved with it? And otherwise, does UCX support or plan to support collective operations, or is it through UCC?
Yeah, they're related, and we debated whether to, and I guess based on your question, we probably should have included a slide or two on it. It is supported by UCX. I think the reason we didn't include it, if I remember right, is we don't have anybody from the team here that is explicitly working with them, and unless Yossi is, and I'm not aware of it, but And then I think too, they're also pretty new. Last year when we ran the first edition of this tutorial, they were kind of like alpha, level. And now I think you can use UCC, but we don't have a lot of good examples to share with you. So that was part of the reason we didn't. But yeah, everybody else who's wondering, UCC is Unified Communication Collectives, and those can use UCX. But a good way to think about it is NVIDIA has these specific collectives that they've used explicitly for kind of machine learning and DGX type machines, and UCC is meant to be a more generalized version of those types of operations. So kind of variations of things like reductions and gather and all gather. But yeah, that's a great comment, David. I think we probably should add a slide related to that, because it will be more important in the future.
Yeah, that makes a lot of sense. And yeah, I haven't been following it, but I know there's a specification, right? I think Manju, the
right. So
leader of this conference is involved.
Yeah. So there are two things that we, so UCC and OpenSnappy is another specification that a couple of people here are involved in, and I think that's another one where it will be very interesting probably in the next year, but right now we don't have any public examples of it being used widely.
Sure.
And I don't think they're quite to like a 1.0 release. So if we say something about it now, then it may change. So.
Sure. Yeah, thanks for clarifying.
Yeah. All right, Matt, you think you're able to do a demo, or we can just take questions and hang out and run examples with people if we like to do that.
I am about ready. Here we go.
Okay.
So I will take back control. Also, I wanted to say thanks to the HPC Advisory Council for letting me use their machine for this. Anyways, so we've got the two different sorts of bindings. Oh, this one uses a much simpler example than the client server one, where we just have a worker talk to itself in Python. So first one is the I must have made a change or something.
I think you have to explicitly run it with Python, I believe, or Python 3 maybe.
Right.
I ran into this recently.
Oops. All right, so it takes a little bit more time to do the setup because we're importing a Python interpreter. Yeah, just does a send and receive and checks that the numbers are equal. So as Jeff mentioned, it uses the async IO module in Python. And so here it's just making an echo server. Here's the async function. Await so that it will block on this. Then we have our send receive, which first makes the server, arranges some numpy arrays, and then does the opposite number, sending and receiving the numpy arrays, using numpy to double check on that. And then just UCP init and run the async function. Very short, simple, considerably less code than our C examples. And this does work with Kupi as well. I've not tried this. Let's see if it explodes. Yeah. Well, that will be a future demo. Anyways. Anyways, this is the much lower level
Mhm.
API. The intention here is similar to the same thinking of UCP versus UCT, where the goal is to upstream this API into UCX proper, so that you get some Python bindings, but then Anaconda and friends can package a more sophisticated version. And so this very much reads like a C programmer is forced to acknowledge that Python object exists. So the blocking handler, that's similar to that. And so explicitly creating the worker, the endpoints. And then you can do tag send, tag receive, and unlike the Rapids version, you end up getting the requests, and then you're manually calling progress down here. But now, the Rapids one, the progress will actually be managed by that version internally under the hood. You can disable it, but by default, you'll get a Python thread that's calling the progress. Now, another important point to note here, the only other Python library this depends on is OS, and that's only used to get random bytes. Other than that, it's all just normal Python, no external dependencies. And so this version should also work with CuPy as well. One of the things that the higher level API abstracts away is this array class. Part of the challenge of making a UCX to Python binding is just the many exciting ways that Python can use buffers. And so with the magic of the Python object model, it will manage all of that complexity for you under the hood, and then you just send a message and not really care where your bytes came from. So does anybody have any other questions about the Python bindings?
I haven't used the CuPy. So what's special about CuPy? That's like is that like a specific CUDA implementation for Python, or?
Yes.
Okay. So just so everyone knows, this is a breaking what is it, late breaking feature that Matt added to his code. So if you look at the examples, they don't have CuPy in them.
Right. It was just something that I thought of would be cool to show off if it worked.
Yeah, no, definitely. We'll get it working for next year.
Mm-hmm.
Okay. So we're coming up on 12 o'clock. So I want to be respectful that people may have other talks. So I'm going to steal the screen back, and we will wrap up here.
Okay.
Okay. Thank you, Matt.
Mhm.
All right. So just kind of to sum up everything, we talked about sort of what is the motivation of UCX, the foundation UCF that helps drive the initial kind of design of UCX, and then the continued development of it as an open source communication middleware framework. We've sort of mentioned at a high level how you can use it to implement things like MPI, transport and link layer protocols. You can use it for one-sided putkit operations for things like SMIM. You can support larger applications with it using the programmer focus UCP protocol layer. And then, I suspect this is not all of the transports and accelerators that are currently listed. We actually need to go back and add RISC-V to the slide now, because now we know that works. But basically most interconnects, are UCX capable. There are a few. I'm actually looking at the other tutorial, and they're talking about OFI over there, which is OmniPath, and I think they may be one of the ones that does not have a interface to UCX, unless somebody corrects me here. And we went through a couple examples. We showed you how to do sort of simple hello world, server client, with the high level API, and how the GPU integration, the CUDA integration can be very simple, and Python sort of, helps simplify that usage as well. So I think that is it. Just to remind you, the website for UCX is openucx.org. They do have a public GitHub with the latest releases of their code. That's what, if you go and pull the examples, you'll pull the, I think I recommended the 1.13 version of UCX. If you have questions, feel free to ask on the Slack. We'll keep that open for a while. Actually, I still have the hot interconnect Slack from last year. So we'll have folks there that we can help you if you decide to work with UCX and have any issues or problems, or you can go to the mailing list, and that's a good place to get further support. All right, so just one more thing, we do want to acknowledge that kind of an earlier version of this tutorial used Oak Ridge National Laboratory resources. Also, I'm running this under the auspices of this Rogues Gallery testbed. So if you're interested in doing something with that, we have a lot of smart NICs. We do have some InfiniBand GPU nodes set up. We also Matt mentioned the HPC AI cluster is a really good place if you are looking to test out these types of application codes. We actually tested most of the examples on the Thor and Tessa clusters within the HPC AI Council. But we also have a test bed at Georgia Tech that has some smart NICs and interesting interconnects. So feel free to reach out to me if you're interested in checking that out. And I believe that's it. So the rest of the slides will be online. That basically just covers the OpenSHMEM implementation on top of UCX. And then it talks more about UCT, which, as you might have seen in Yossi's presentation, is pretty low level. But if you're interested to learn more, then all those slides should be on the GitHub website. Okay. With that, I'll leave it to any further questions. I know this is kind of an interesting Zoom event thing, since you have to post them on Slack, but feel free to reach out to us there, and we'll read them out. We'll hang out for a minute if anybody has questions that they want to kind of one-way communicate with us. But thank you everyone for attending, and we hope to see you in one of the UCX forums or mailing lists in the future.
Thanks very much, Jeff and team. That was a great tutorial. And yeah, like you said, the Slack channel is very asynchronous. You could answer that. I didn't realize we could still, did you say interact with last year's?
Yeah, they
workspace?
actually, I think what they did is they archived all the
Right.
channels from last year. But I do appreciate that this is a there's a challenge that's like every year you don't want to create a new Slack workspace for every year. So I think they did it correctly in that they kind of archived everything and they added all the new channels for this year. So
yeah, I think I heard 90 days from now they'll archive it, but I may be wrong about that.
Yeah,
that might be a Zoom thing. But yeah, thanks for bearing with the technical difficulties as well. And you guys did a great job staying on time.
Oh, well, thank you. Thanks for your help. That's let's see, I guess we can stop recording here.
Yep. And just to remind everyone, we have a lunch break now on the track 2 of tutorials. And at the top of the hour, we will talk about OFI libfabric.